Hey everybody, welcome to Bearing Lubrication and Health Insights Made Simple. We'll just give everyone a few minutes here to get on and get settled in before we get started. So before we dive into the content, I'll give you a brief overview of myself. You'll be listening to me the next 30 or 40 minutes. So my name is Blair Fraser. I am a CMRP and CRL. Spent last 20 years in maintenance and reliability, with the last about 12 years of that focused on the technology side. And before that time, I was an end user, being responsible for equipment in various industries. Over my career, I was able to co-found a artificial intelligence company called Cortic.ai. I'm a co-host of a podcast, hopefully you guys have heard of, called Maintenance Disrupted, and is also an adjunct professor at the University of Wisconsin, the Connected System Institute. Um, so as I look out in the ecosystem of IoT, and specifically as we look at this from a bearing monitoring point of view, I used to be able to count on at least both of my hands, the number of vibration sensor companies that are out there. Now, with the advent of MEM sensors and easier to connect data, of course, that number has risen to hundreds and if not thousands, right? And really, as we look at this, there seems to be a solution for every single problem we have out there. But really the question is, are we even focusing on the right problems to begin with? So when we think about IIoT, which is the industrial Internet of Things, we think of this, going back, at least I might date myself here, but back to the, early Star Trek days when, information was coming out to us. I mean, we have this idea of having this command center with all this information coming in. But the reality is, where we're at in our data journey is we have enough data, we're generating enough data. What we need more of is insights, right? So often what you're seeing in front of you on this screen is, this is information overload. There's too many charts, trends, things to look at. Really what we often need is not what we want. We want this flashy things to look really cool when someone walks by. But really what we need is actionable insights, right? And when it comes to bearing in particular, of looking at the lubrication and health needs of a bearing, right? This is often what we need. We need something just to tell us very prescriptively what we need to do to change that course of action. An example here is this specific bearing needs lubrication, right? Yes, we can display that in fancy graphs and make things pop up and flash, but really it's the insights that we need to drive action is what we should try to get. And that's really what I'm going to talk about today is not saying we've been doing it wrong, but would challenge maybe we're focusing on the wrong things when it comes to monitoring the health and needs of our bearings. So when we look at this, and hopefully you guys are familiar with the traditional P to F curve, where it looks at the asset condition or health of that asset over time. Now it's important to note a proper P to F curve is based on a single failure mode, and an asset or a component will have multiple P to F curves. But what we're looking at that is going through the design, the installation, and then essentially that proactive, predictive, and reactive domain. And when we look at bearings in particular, right, is there's the a focus happening, and what I see in particular, there's a focus happening in our industry right now to race to find the onset of failure at the earliest possible point, right? So something is going wrong in that bearing. Who can detect it, and how can we get that information to that person? And I think that's great, right? Is once a failure started, it is important to know, when that failure started and how much time we have left for remaining useful life until it starts to affect our operations and things like that, right? And I don't want to get into that debate of technologies and who's first to detect what on this P to F curve. Really what I'm trying to set out here and challenge that mindset of thinking is, it goes back to that saying, an ounce of prevention is worth a pound of cure, right? Is there things we can do to the left of that predictive domain into that proactive domain to help reduce failures from happening in the first place? Because if we think about it, in that predictive domain, and that P on that P to F curve by Nolan and Heaps is a identifiable physical condition that's indicating that that asset is starting to fail. So it's an identifiable physical condition, which means it has to start failing before we can pick it up. So it's already started down that path we don't want it to go down. So is there stuff we could be doing in that proactive domain to change the course so it doesn't get into that predictive domain? And of course, as we're talking about bearings, we know what this is, but can we start to focus more of our time and effort on it? Right? Now, when it comes to identifying failures on that P to F curve, right, is, ultrasound owns the apex of that P to F curve for bearings, right? Now, one of these is our P to F curve that we promote on our website, and the others is by other industry consultants and things like that, right? And I don't think it's goes into very long debate or very much debate about ultrasound and its value proposition. Now, it's often seen as that first sign of an issue once a bearing starts to have those conditions. But really and this goes back to a study a long time ago, that typically, and if you think about it, what we're doing with ultrasound is we're listening, we're measuring for friction. So what many studies have shown, and these studies often get reproduced year over year in the academia space, is that ultrasound we'll be able to detect a change or what they call an incipient or initial stage of bearing failure before there's a change in vibration or temperature, right? So it does really give us that advanced warning notice, but in that signal that it's doing, measuring that friction, we can also use it to really own that proactive domain. So when we look at ultrasound, what is ultrasound doing? And it was interesting, I just read a study yesterday from Plant Services magazine that indicates that ultrasound is actually growing faster than vibration in terms of a condition monitoring technology. So more people in their study plan on implementing ultrasound than vibration, which I think obviously from a UE system, so that's perspective, but it also speaks to the power and simplicity of ultrasound. So what we're doing when we're monitoring when we're putting an ultrasound sensor, now all ultrasound sensors are not created equal, and there is a difference between acoustics and a microphone and an ultrasound sensor. So we're starting to see with the advent of IoT and specifically the low cost of MEM sensors saying, oh, I have ultrasound in this or I have acoustics in this. And you do for a certain point, but do you have the sensitivity and the frequency range that we need to look at from this friction point of view? So what we're doing is when we mount a sensor, I'll quickly hold it up. This is one of our ultrasound sensors. It's called our Ultratrac 750 sensor that gets mounted to a bearing. And what it's simply doing is listening to that bearing. It's listening for the signs of friction and impacting, right? And what's interesting is when we think about this, and it goes back to Nolan and Heaps again with that P to F curve, is what they fundamentally taught us is that doing maintenance or making decisions based on the condition of an asset is a lot better than doing it on time. But yet, for our bearings, and specifically lubrication, we're still doing it on time and not the condition. So without a doubt, the condition of that bearing is proportional or directly proportional to the friction in that bearing. So the value of vibration, we are a big believer in vibration. We are UE Systems, we're a big believer of having a toolkit of available condition monitoring and strategies is what is going to set the difference for you and your assets, right? The reason I wanted to bring this up was when you think about vibration, essentially what we're doing in the simplest terms of vibration is we're measuring displacement, we're measuring movement, right? So something has to move, even very subtly, before vibration is going to pick it up. So what we're doing with friction and ultrasound is we're picking up those subtle changes in impacting and friction versus movement. So that's why we're able to pick up a lot of these failures before vibration, right? Is because we don't have to wait for this thing to physically start to move, right? Whereas vibration, you would typically either put a triax sensor in, right, to measure all three axes, because you're trying to measure movement in different directions, right? Where ultrasound is very directional. So if you think about this, if you were to listen to a bearing just with your ears, now of course this is in the audible range of a human, you would fine tune it. You would say, okay, sound's coming from that way, right? And start to hone in from that point of view. So sound obviously comes out. So what it allows us to do with ultrasound is mount in locations and areas where we're not concerned about different axes and things like that. So let me give you this hypothetical question, right? Do you agree, even without identifying the exact cause of a fault, there is great value in simply identifying that maintenance is required, therefore avoiding catastrophic failure and the potential for secondary damage, injury to personnel, and excessive downtime? So is there value in knowing that something's wrong, even if you don't know the exact fault? And the reason I'm saying this is because I firmly believe that, from a vibration point of view, is identifying the root cause or the fault. Is it an inner race defect? Is it an outer race defect? With technologies like modal and ODS and those type of things, right? Is you can get down into the weeds. But my question to you is, does your action based on that data change whether it's an inner race defect or an outer race defect? Most of the customers we talk to is no, right? We will use that data in a root cause analysis to try to engineer out or eliminate the defects that are causing this, right? Which I think is fantastic. But in terms of the direct action you're going to take is no, I'm going to replace that bearing, right? And what we found is, as we see the advent of IoT start to really push us to stop taking away from route-based data collection, is, typically people walk around with a handheld analyzer and take data on a monthly route-based data. And what we found through our studies and industry studies that on average, 80 to 90% of the data we're collecting is on equipment, on machines, on bearings that have no impending issue. So they are healthy, there is no action required. Now, from a reliability, asset utilization, uptime point of view, that is fantastic for you. Now, from a business perspective, you're spending a lot of time, resources going around to pieces of equipment that don't need their data collected, right? Now, there's always an advantage of having a human out there. As much as I am a fan of technology, and I do believe technology has its place, is, we're not at the point now where we're ever going to replace a human putting physical senses out to things, right? There's, certain things people may be able to pick up by doing routes. Is it leaking? Is it dirty? Things like that, right? But on average, 80 to 90% of time, we're collecting data on machines that are healthy, right? And that's really where the IoT part is coming in and simplifying, how we're managing our bearings, right? In fact, now I will get into this a little bit later, but study after study shows, now this is a study by SKF, but this study has been reproduced by industry analysis and other bearing manufacturers, that the smoking gun of premature bearing failure is lubrication related issues. There's no doubt about it. Now, this study showed that over 80%. I've read some other studies that show 60%, 70%, right? Regardless, whether that number is 80% or 60%, it's still the obvious cause that we can start to address in that proactive domain. So I'm going to challenge the mindset of thinking here a little bit. I want you to imagine this, that you could walk up to any bearing in your facility and ask it just one question. Just one question. So you can't go and ask for more questions and things like that, right? But imagine you could walk up to a bearing and ask it just one question. What would you ask it? I'm going to let that sit and percolate for a minute. So I get, typical answers. When are you going to fail? Right? Or what are you going to do for me today? Right? Or even how are you feeling? Right? So those are some good questions to ask, right? But let me flip it on its head, because what you probably just answered in your head or in the chat here is likely, and no offense to anybody, this is just human nature, a very selfish question, right? We put those bearings in place. We want them to spin with as little friction as possible, right, to do what it needs to do. But if we flip that question on its head, imagine that bearing could ask you a question. What do you think it would ask you? Right? Isn't that an interesting? We're flipping that whole scenario, right? And what it's going to ask you, I think, is a better question to answer than what we would ask it. So what would it probably ask you is, hey, when are you going to grease me? I need some grease soon. Or, you're starting to operate me outside of my design parameters. Things like that, right? Is, we got to flip it on its head, the question on its head. And that bearing is talking to us. It is trying to ask us questions or tell us information. We just need to be able to listen to it, right? So the whole point of an anti-friction bearing it's in its name, is to control, reduce the friction of rotating pieces of equipment. So by monitoring that friction, which is the condition of that bearing, we can start to identify things like poor lubrication, which includes too much and too little lubrication, rubbing or skidding of the rolling elements against the bearing raceway, impacting due mechanical issues, right? So by measuring just one variable, the friction in that bearing, we can get some very simple but very useful insights from that bearing. So let's go back to that study where they said over 80% of premature failures can be traced back to a problem with lubrication. Now, if anyone wants to reach out to me, happy to send you this study. It is in the public domain. And what it talks about is they break that 80% down into 4 categories. Insufficient lubricant quantity. Often when we read about this or when we think about, that 80% of premature bearing failure, are we, lubricating enough? Are we giving it enough, right? But that is actually the smallest part of that 80%. We start getting into a long time without renewing, unsuitable lubrication, so mixing greases, putting the wrong grease type, oil type, things like that, and contamination, lubricant contamination. We know what dirt, grime, water does to our lubricant. It essentially breaks it down, right? So we need to look, when we're starting looking at that proactive domain, we need to look at all 4 of these categories that are causing that premature bearing failure to truly make it simple and easy to monitor the health of our bearings. Now, what's happened with lubrication as we focus on that proactive domain is, we've gone to great lengths to make sure from a mathematical or theoretical point that we start to lubricate as accurately as possible, right? Now, this happens to be a NORI calculation. There's one by SKF, and I think they're fantastic calculations to get you into the ballpark. The challenge is a lot of our factory floors, a lot of our machines are being asked to do things differently on a day-to-day basis. And I'll give you an example here. If you look at this calculation, there's a parameter called N equals speed. How many of us have assets that rotate at different speeds, right? More and more we're seeing single speed motors getting transformed into or retrofitted into variable speed drives. We're seeing control valves go away and variable speed drives and things like that. So speed has a huge impact, and that obviously makes sense. The faster it spins, the more rotations, the more lube it's going to need eventually, right? And also, all these correlation factors, right? Give me an example. Here's temperature. The first one, temperature, housing below 150, and the next one is 150 to 175. What if that correlation factors or that bearing housing is 151? Do I use a correlation factor of 1 or 0.5? In fact, I should probably use like 0.93 or something like that. And the whole point I'm trying to make here is that our variables we are using to make these calculations often don't reflect what's actually happening in our operational environment. So what we do, and this is the main driver of the simplicity of our systems like the OnTrack, and using ultrasound to monitor that very telling condition of friction in our bearing. And the reason I reference this is often people look at this and say, this is too good to be true. It can't be that simple. Now, we say it's so sophisticated, it's simple. So what's happening in these sensors here and how it's measuring that ultrasound, trust me, it is not simple. But how the information gets to you is very simple. So what we do, and this is an ISO standard, ISO 29821. And what it talks about there is once you set a baseline, now, obviously, everything is dependent on that baseline. And I can go into a lot of information on how you set a baseline, particularly how do you set a baseline on a bearing that's already been lubricated, it's already been operating. Not too often do we get a brand new, healthy, well-lubricated bearing come into our facility. So what we see is we see an 8 decibel increase in that friction. So to us, the decibel reading is a friction reading. So if we see an 8 decibel increase over baseline, is an indication it requires lubrication, right? And what we're doing here, and it's important to note, is that 8 decibel it's not screaming, it's not going to be any difference in temperature, it's not going to be any difference in vibration and movement. It's that thin layer of film on the rolling elements is starting to degrade. So it doesn't mean that at 8 decibels you have to rush out that minute and start to lubricate that bearing. What it means is we've starting to lose that film, and it's a good indication now is a good time to go lubricate. And what people start to say is, okay, Blair, if I get this in the middle of the night, do I need to go out and lubricate right now? No, typically with any other technology, you're not going to pick up even the slightest change in this friction. Once we see a 16 decibel increase above that baseline, indicates we've gone beyond that failure mode, that lubrication failure mode. Right? And we're entering that P to F curve at that point. Often that 16 decibels, you are not going to pick it up with any other technology. And we've actually had some feedback as this is so early on, I'm not going to do anything about it. And I think that's great. This is an indication that something's going wrong. You can then, bring out supporting technologies to start to measure oil analysis, start to measure vibration. Again, at this point, it's related to friction. And what's great about friction is I don't care if it's an inner race defect, an outer race defect, an issue with one of the rolling elements, with the cage, right? The more friction, the more likelihood of failure, or the more I can track it entering that failure mode and getting to that F on that beat F curve, which is the functional failure. Now we see a 32 decibel increase over that baseline. It's a critical failure. So this is when you start to need to start to plan to have some immediate action in the near future. So this is the easiest way I can start to describe, and really the title of this is to simplify. How do we make bearing lubrication and health insights simple? This is one of the ways we do it in our UE Insights with our on-track product. Let me walk you through this. So imagine you have hundreds of bearings, and you probably do, hundreds if not thousands of bearings in your facility, right? And you want to know the condition of them all. What you don't want to do is look at squiggly lines where you have to stand on your left foot, bite your tongue to the right, and go like this, and then go, I think I see this, right? This is very intuitive to use. In fact, what we designed this for is even people that don't necessarily have a technical background. You don't have to be an ultrasound, you don't have to be a bearing expert, right? It's very easy to see this. So in this case, this bearing, it's on the non-loaded side or the non-drive end of a motor. It's reading 28.7 decibels. Its baseline decibels, as indicated by the start of this green, is 26 decibels. So my friction is slightly over baseline. It's in that green zone. Perfectly healthy working bearing. Do nothing, right? We don't want you to fiddle with it. This is ideally where you see all of your bearings, but the reality is you are not going to. Okay, so when we see, and I want you to imagine with me, that arrow is actually straight up, 90-degree angle right into that blue zone, which will bring us about 40 decibels, right? Is an indication it needs lubrication. Now this is where the power of IIoT comes in. So can you imagine this bearing requires lubrication? Now I ask you to put your eyes on me in particular. I have this running on my phone right now. I can see this, and I walk up to this bearing using my phone with a grease gun and start squeezing grease into that bearing. What you're going to see is as that grease starts to get into the bearing, that friction is going to start to go down and go down and go down, right? So we're intuitively watching as grease is hitting that bearing, that friction to get reduced. Now what we do is we take data while we're lubricating every second and send it to any device anywhere, right? So what you're going to actually happen is as you're lubricating that bearing, if you think about it, you have a bearing, and typical lubrication ports are on the top, you squeeze a bunch of grease into there, that grease has to disperse into that entire bearing. The way it's going to do that is the rolling elements are going to go and start smushing it around through that. So what we actually see in real time is as you apply grease, you see a small little ding. That friction will increase very quickly and then go back as that grease starts to go. And that's how we know grease is hitting the bearing. And what you would end up doing is start to apply grease and watch that friction fall. And I'm doing this very slowly. In fact, the friction falls very, very quickly. And what you want to do is apply a little bit of grease, wait a little bit, apply a little bit of grease until that arrow hits that 26 mark, right? You've restored that bearing friction back to its baseline values, its happy spot. You stop lubricating at that point. That means you have optimally lubricated that bearing. In fact, what we find is when you start using insights like this to perform your lubrication, so ultrasound or condition-based lubrication, is you will reduce your grease consumption by 30%, I would say at a minimum. Now it depends how much you've been over greasing in the past. Now imagine this situation. You hit 26, you've restored that bearing friction, and you keep on greasing. Obviously not recommended, but you keep on squeezing it in, right? Keep in mind, a grease gun can put about 10 to 15,000 PSI. So you can squirt grease and blow those seals right out. So as you start to overfill those cavities, remember, from a rolling element bearing, we don't want to fill the entire bearing with grease. We just want to coat the rolling elements with the lubrication. So as you start to overfill that cavity, your friction is actually going to go up. Those rolling elements have to fight the friction of over and overfilled. So if you keep on lubricating after that 26, you'll actually see that arrow start to go up at a rate about 10 times the rate it came down. So you're going to put one grease, it's going to go like this, it's going to go this. You can actually overfill that grease till it goes into the yellow zone, right? Now, I talked a lot about greasing, but what about from just a health insight, right? So imagine that arrow was, so I'm going to say 50 decibels, right? So we're in that yellow zone. Indicates we're beyond lubrication. In fact, what we see is you can apply lubrication to temporarily reduce that friction, but if it's a, you know, a scratch in the outer race, you'll temporarily fill it with lubricant, but of course, every time a rolling element goes across it, it's going to carve it out, and you're going to see that friction. So you can mask it. We'll see it kind of go into the blue and then go back into the yellow zone really quickly. It's an indication that, we're beyond a failure, we're beyond the lubrication failure mode. At this point, I tell people, don't worry about the numbers. Scratch all the numbers off of this. What you're looking for is that rate of change. How quickly is that arrow falling to the right? And what that tells us is the failure, the failure rate of that. And again, I said this before, I don't care what the failure mode is, most every failure mode in a bearing leads back to friction. So if that friction is starting to increase and starting to go like this on a daily basis, you know the trajectory of how quickly that bearing is starting to fail. So how simple is it to see bearing health insights from friction? Okay, so this is the case study I'm going to show. This is on a cooling tower. It's a belt-driven cooling tower. You can see our sensor there. It's the same one I showed you. It's called our Ultratrac 750. This is going back to our on-track system, which is remotely monitoring that friction anytime, anywhere, right? So it's a cooling tower, very typical application. This is actually the trend that I took a few days ago from this bearing, right? And what you're seeing here is, first of all, there are 4 dash lines. Now, the green one at the bottom is hard to see. That's actually the baseline friction, which is sitting at, I believe, 9 or 10 decibels, right? And you can see the solid blue line that's kind of floating above it. That's actually that real-time friction taken every minute from that bearing for 24 hours. This is a healthy friction trend in that bearing. That blue dash line above it, which is 8 decibels above that, is the lubrication friction level, the need for lubrication. If that blue trend line was to go above that blue dash line, we need to start lubricating that bearing. Now that yellow is the warning and the red is the critical. This is really how simple it is to monitor the health of your bearings, right? We're trending a friction time series value. This is ideally what we'd see. Now, the reality is, a lot of our bearings, we don't see this right away. So when we take a closer analysis, now you don't have to do this, right? But what you're going to find, if you were to plot this on a histogram, you're going to find that obviously that friction is trending near that baseline, so it's not waving around. Now, this is probably one of the most questions, or the most common questions we get asked. I have a variable speed drive. Won't my friction change? Okay, so a lot of research has been done for this. And again, I welcome, if you want to read the study, we have some studies here I can send to you where friction was, or ultrasound was trended through varying speed drives. And what we find, and this is fantastic about friction, regardless of the speed, friction should remain constant. There's a caveat there. In a healthy, well lubricated bearing, regardless of the speed, the friction should remain constant. Now we do see maybe a 2 or 3 decibel change, right? Which may make us have to change our alarm limits a little bit from, the lowest speed possible to the highest speed. Even on a well lubricated, we might see a slight increase in that friction, right? Now, as we're talking about a healthy bearing here, is when we do not have a healthy bearing, that completely changes. We see a huge, so obvious impact on that friction. So, and what we see here too is we don't see the peak to peak values change. So we can have an average value hovering around that baseline, but we don't see a lot of jumping up and down, which I'll show you exactly what that looks like. So wait, doesn't friction change based on varying speed conditions? As I talked about, no, right? And I'm going to show you what this looks like with some trends here. So we do see a slight increase. Now, if it's an unhealthy bearing, we see a big increase, but that change in decibels should not change too much throughout varying speeds. Okay, so remember that. So what does the trend look like in an under lubricated bearing? Okay, so this was a case study. We put this sensor on for about an hour to gather some data. Within an hour, I can say, I can start to see relative condition and needs of those bearings. So our initial friction was at 14 decibels. We had a peak to peak, so the max reading and the lowest reading within that certain time window, right, was close to 7 decibels, which is a bit high. That's a little bit concerning to me. And what that tells me, if I was to zoom into this, and I do have one I'll zoom in here, is if you were to look at the actual trend, you can see it bouncing around. Now imagine you're playing an audio off that bouncing, you would literally hear static. And what that's an indication to us is, that bearing requires lubrication. Now what we were able to do is, this is actually our smart loop system, which uses these. You might have seen these or used them in your facility. They're referred to as automatic or single point lubricators. What we've done is we designed our own called the the M-UE lubricator, which is designed specifically to work with our smart loop system. So in this use case, we were able to monitor the friction, and through my cell phone, in fact, I used my computer, I was able to apply and tell this thing remotely from hundreds of miles away to actually put a little bit of grease into that bearing. So I put 15 cc's of grease into that bearing. What was actually happening was I had to fill some remote lubrication lines and things like that, but I did it from the comfort of my home. And what we noticed after we remotely greased this, we saw that baseline friction drop from 14 decibels down to 11 decibels. And we saw that peak to peak, so the bouncing around that we get, down to 3 decibels. Okay, and what we did is they had a planned shutdown, so we brought it back up. And we applied a little more grease, and we actually were able to reduce that friction down to 9 decibels and that peak to peak down to 2 decibels, all remote, right? So now we have a healthy, well lubricated bearing. And I should have noted at the start of this, this is on an HVAC unit, a varying speed. And during this time period of 24 hours, this went through every speed possible of that HVAC, and you'll notice there is not a large change in the friction or decibel readings. This is how simple really it is to lubricate and to monitor the health of your bearings. So when we look at an under lubricated bearing, if you dive deeper into that, right, the graph on the back end here, where hopefully my mouse cursor where you can see it, is we do have a nice bell curve on this histogram. What you notice is there is one center point, but the other 2 points beside it are close. So what we want is, regardless of the speed, is we want a nice center point into that, right? So not only did we see a decrease in the friction, but we also saw a decrease in that peak to peak value, which we can notice here, right? Our center point went from, I think, 14 down to 9 decibels, right? Our minimum was 7.8 and maximum was 11.5, it looks like, where on the other side, our minimum was 11.95 and our maximum was 18.7. So quite a big difference in those peak to peak values as well. So friction trend in an under lubricated bearing, okay, is you can notice here a decrease in friction the moment grease hits that bearing. Now, one of the challenges, and we set out to be able to disrupt bearing lubrication, is being able to lubricate very precisely with using these single point lubricators such as the MUE lubricator. But we need confidence. We need confidence that grease is actually hitting that bearing. A lot of the challenge in the survey we did with these single point lubricators, of course, they're based on time, which doesn't impact the condition of the bearing. But of course, if the grease cartridge here was to run empty, the battery was to die, there's a lot of reasons why grease, cannot or sometimes doesn't reach the bearing. Is we know grease is hitting the bearing because whether good or bad, we see a change in that friction. So in this case, we added 4 cc's. You can see that change in friction after adding 4 cc's, right? We added another 3 cc's, and we kept on seeing that friction level drop. Again, we saw the friction level drop. We also saw that crackling, those peak to peak values start to drop. So it becomes very obvious once you install a friction sensor onto a bearing, generally what is its health, and is it asking for something? Remember that question, if that bearing could ask you something, right? It is asking you. It's just speaking the language of lubrication. So here's a friction trend in a bad bearing. So let me go back. No, I can't go back. So let me just stay here. As you can see from that nice trend line I was showing you before, right? Hovering around that green line, not too much peak to peak. This is a bad bearing, right? We put the sensor on, we let it run. This is, unfortunately, a bad bearing. Now you can imagine if each one of those dots, which is a reading, was to play you a sound, right? It's going to sound like crackling, and that's exactly what that bearing is doing. Now the friction isn't increasing, but the peak-to-peak values are, which is an indication it needs lubrication. Now what we'll see if we do not lubricate it is we'll see that friction start to rise over time, right? So if we look at the histograms of that, what we'll notice is, and if you notice this trend here, you'll see that friction increased day after day after day. I think it was a 4x times in 4 days how much that friction increased here. Though I think we started at a peak range or a mean of 4, and we ended up with almost 14 decibels. So a huge increase in friction. This is a bad bearing. Becomes very, very obvious, right? I don't know if it's an inner race defect. I don't know if it's an outer race defect, but I do know it is a bad bearing. So when we get into this about simplifying, the whole point of this presentation was to simplify it. I'll go back to that first statement I mentioned was we need actionable insights. We don't need data. So here's an example of an alert that comes in: lubrication required on this specific bearing. Use this type of grease. Right? I don't care if you're a lubrication expert, you're an ultrasound expert, or you're a planner and scheduler that's just going to enter these work orders in. It's very prescriptive. No data overload, just simple, actionable, prescriptive alerts. This bearing requires lubrication. So as I mentioned, everything is really about setting that baseline. So a lot of thought has to go into setting that baseline. We recommend 3 different ways of setting the baseline: setting while lubricating, historical, and comparison. So with the addition of the smart loop and being able to do this remotely, this really changes the game. So when you install a new system, you have these lubricators. You can grease at any point in time, or it'll automatically go and grease for you by measuring friction and restoring that friction. So we would always recommend setting while lubricating. So what you would do is you would put a small amount of grease. Now these MUE lubricators, I'll bring this back into frame, can output varying sizes or varying amounts of grease coming out of it, as low as 0.33, so a third of a cc. That is like half a teaspoon. Right? It's a rounding error on typical grease guns, right? So when we say apply a small amount, we literally mean apply a small amount, right? Is you apply a small amount, and 3 things are going to happen. First, if you see that friction start to reduce, it's an indication that that bearing was under lubricated and needs to be lubricated. So in that case, we'd apply a small amount. If there was no change, I might apply it again just to see, right, to make sure bearings actually, or grease is hitting that bearing. Now, as I mentioned, if it's under over lubricated, we will see a slight spike as soon as that grease hits that bearing. So we at least know if you have remote lubrication lines and things like that, it's getting all the way through those lines. So it's an indication. We will continue to grease until we've hit a point where that friction starts to go up, and we would set the baseline right there. Okay. Now, if we apply that small amount of grease and that friction instantly and sustainably increase, even by a few decibels, it's an indication that bearing is it's already over lubricated, which does happen even on new bearings, right? That day, and I'm sure we've all done it, where you packed a bearing, you put grease in your hand and you whack it in, right? You can over grease that way, right? So it does happen where even a brand new bearing is over greased. Now there are times when that friction remains constant. It doesn't happen a lot, but it means it's ideally lubricated, right? So we don't want to sit there and put too much grease in. What we'll do is we'll leave it at that baseline and use the historical method. And what we do there is we let it trend for over 30 days, right? We set up alerts just to make sure we'll catch any failures in those 30 days, but we'll let it sit there for 30 days and we'll monitor, did that friction increase? And we say if there's less than an 8 dB increase, then that is a very good baseline to set it. Now you can use the comparison method. If you have similar assets, similar bearings, same speed, same load, we can start to do the comparison. Why is this bearing generating more friction than this one, right? And then we set it comparison to either what it was or its brothers and sisters on the same asset or different assets. Of course, we are here. We do this day in and day out. But it is relatively easy just to set that friction level. We are happy to help with that. So bearing lubrication and health monitoring made easy with friction. So the moment you install an ultrasound sensor, measuring that friction, measuring that impact, look for a consistent average trend value, right? look for a nice steady line across all operating conditions, right? Look out for those peaks and valleys, those noise that we see, right? While the friction might be there, this is a good indication that's bouncing around, right? That it's starting to impact, right? And that can tell us a lot. And look for, a lack of increase over those 30 days, right? If the friction's starting to increase over 30 days, there's something going on with that bearing, right? It shouldn't be, if we think about how our bearing fails, right? The closer we get to that functional failure, that F over time, the higher the friction is going to be. It's like a battery dying. A battery dies like this and then just drops off, right? So that's what we're looking for. It is really that simple to do. So I do appreciate you taking the time going through really how I believe that monitoring the friction is a growing condition to start to monitor your bearing and lubrication insights. And I invite you, if you want to learn more about the use case that I just presented to you, see the data come in live, book a 1-hour demo with us. Go to the link here or go to uesystems.com/smartloop and take a look, book a demo. We'll actually walk you through using live data on live systems and show you what this data looks like and really how simple it is to do this. I thank you for your time. Feel free to reach out directly for any questions.